Thank you for the introduction. So I'm Tunam. As you heard, I'm a PhD student at Georgia Tech, and this is going to be my presentation on the interactions of calcium sulfoaluminate belite cement with alkanolamines as an admixture. So the motivation for this, as you all know, is that our industry has a fairly large carbon footprint, and we're trying to reduce that. You've heard this many times throughout the convention, but just a little bit more on that. One way to do that is to use more lower embodied carbon cements, such as Portland limestone cements, type 1Ls, and blended cements, such as Portland cement with fly ash, blast furnace slag, and silica or silica fume. However, there are a couple others that haven't really caught on in the United States yet, such as limestone calcined clay cements and calcium sulfoaluminate cements. I just wanted to point you to the graph on the right. We're going to look at calcium sulfoaluminate belite cements, which lowers that global warming potential around 33% when compared to ordinary Portland cement. And we're wondering if we're using these lower embodied carbon cements, if we can use the admixtures in the same way to tailor lower embodied carbon cement performance. So some commonly used admixtures in Portland cements are like dispersants or superplasticizers and set controllers such as accelerators. So what is this CSAB that I'm talking about? It's a combination of calcium sulfoaluminate and belite. So calcium sulfoaluminate, or in mineral form yelemite, reacts with added anhydrite for the sulfate balance, along with water to form ettringite and aluminum hydroxide in a similar fashion as your C3A or aluminate reaction. And belite, the same one found in Portland cement, reacts with water to form your calcium hydroxide and CSH. Applications of calcium sulfoaluminate belite cements are similar to type 3 Portland cements, so you can find them in cold temperature construction or pre-stressed plants. It's also shrinkage compensating, so it's good in flat work where you want no joints and large floors such as in warehouses or data centers. On the bottom here, I just have a couple of EDS graphs of a unhydrated and a hydrated sample. Just to highlight the difference that the C2S does react a bit later. So we have on the right, after reaction, we have ettringite and aluminum hydroxide, but some of that C2S stays unhydrated and hydrates later for that later age strength. On the right, I just have a quick pie chart of the phase percentages. We can see our main three phases, that yelemite or the CSA, the anhydrite, and the C2S in those colors. And we have a couple of minor phases in our sample. So the objective of this study was to look at how alkanolamines, when used as an admixture, affect CSAB hydration in early ages by looking at phase formation, structural buildup, and microstructure. And why we chose alkanolamines is that they're commonly used in Portland cement already. They've been found to increase compressive strength and increase degree of hydration. I just have a quick graph of the calorimetry curves on the right, just as reference with Portland cement and the alkanolamines that we're using in this study. What are alkanolamines? What are this big word that I've been saying and messing up with a couple of times? So they're a product of ethylene or propylene oxide and ammonia. The two most common in our industry right now are triisopropanolamine or TIPA and triethanolamine or TIA. Also used in this study is diisopropanolamine or DIPA. I have those structures on the right if you're interested in those. And they're commonly used in Portland cement as grinding aids, so we want more efficient grinding, use less energy, and also have more even grinding. They're also used in Portland cement when admixed as a set controller to like reduce or elongate the setting time and accelerate or decelerate hardening. And then really quick on the specific materials and methods in this study, the CSAB was commercial from the Netherlands. The alkanolamines are commercial grade and are of greater than 99% purity. We used a 0.45 water cement ratio in this study, and also a 0.02% alkanolamine by weight of cement, as those are commonly used in practice and also in literature. And I chose 5 methods to study these early age properties. So isothermal calorimetry for rate of hydration, in-situ quantitative X-ray diffraction, and thermogravimetric analysis, both for phase formation. amplitude-sweep oscillatory rheometry to study your rheology and the storage and loss modulus, and scanning electron microscopy for looking at the microstructure. So to get right into the data, here are the results from the calorimetry. If you kind of remember the curve of Portland cement earlier, I have two graphs here, one showing the same data, one's just zoomed in of the first 6 hours, and the other is the 0 to 24 hours hydration. We see our control sample in black, and then the TIPA, DIPA in red, green, and blue respectively. Looking at the first graph, we see some interesting behavior where the sample containing TIPA actually doesn't really shift that first peak both laterally or vertically. Is that the same? But the samples with TE and DIPA actually delay that main hydration peak a little and reduce the heat. If we look a little bit at the beginning over in this 1 hour time period, we also see that there is a longer latent period with the alkanolamine containing samples, which means that there's a little bit more time before that onset of hydration. And a lot of us know that CSAs react super fast, they set super fast, and usually to offset this, you can add extra sulfates, so more gypsum or anhydrite, but that does increase the risk of deleterious expansion later down the line. And this may be a way of getting a longer workable time without that expansion later on. All alkanolamines also enhance this shoulder out here, so more reaction there, but they do decrease that heat on the right side between 9 and 24 hours and decrease the total cumulative heat. Really quick before we get into the XRD, as that's a little bit different than what you typically do with powder XRD, we actually did this in situ on a benchtop XRD rather than what's usually done at a national lab. Just more on that is that we mixed the sample, put it in the standard sample holder. We had some Kapton foil to cover it to prevent any drying while the sample is hydrating, and then we held that in place with a metal ring. Down here, I just have some example scans. This is about 1/20th of the data for one sample, just showing that throughout the different scans, we see changes in the phase and the peaks, and that's what we use to study our phase formation. Okay. So on the right, I've picked out specifically two phases rather than choosing to show all of them, as that would be a little bit convoluted. I chose yelemite in the solid lines and ettringite in the dashed lines. If we look at the ettringite formation between 0 and 6 hours, we see a slightly slower rate of formation, but more significantly for the following 42 hours, and especially in that TIPA sample. There's also a decrease of yelemite dissolution in the TIPA containing sample. You can see that as the extra hump out around 12 to 24-ish hours. And if we look at the very end, at 72 hours, we see a greater yelemite consumption. However, if we look at the ettringite formation, we also see that there's less ettringite, which is interesting because if you're reacting more product, you'd expect to have more, or reacting more reactants, you'd expect to have more product, but we don't see that in this case. And then really quickly on the other phases, the anhydrite showed a similar trend as the yelemite, so there's a decrease in the dissolution rate, and there's a greater consumption in the alkanolamine samples. Interestingly, we saw no change in the C3A over the 72 hours, and expectedly we saw no change of the C2S in the 72 hours. And early age phase formation is important because it gives us some details about the early strength and then the total dimensional stability. So getting onto some TGA data, this is looking at almost the same data, except we're able to also see aluminum hydroxide on the right. And we can't see that in the XRD because it's largely amorphous. And in general, if you have more hydration product, you'd have greater strength. So the alkanolamines affect the ettringite more than they affect the AH3 in this case. if we look at TIPA, it looks to have a greater effect than the TEA or DIPA containing samples. And if we look at our 6 hours versus our 24, 48, and 72-hour marks, we see that they behave a little bit differently, where the TIPA actually increased both the ettringite and AH3 formation at that 6-hour mark, but decreased in later stages, while the TEA and DIPA containing samples have little to no effect at that 6-hour mark. We have less at the 24, and in the case of ettringite, we actually have an increase of hydration product at the 48 and 72 hours, which is different than what we see in the XRD data, which might imply that there may be low crystallinity ettringite. So we can't see that in the XRD, but we can see that when looking at TGA. And now really quick before we do the rheology, this is a little bit different than your standard rotational rheology in that it's oscillatory, and we're increasing the strain slowly over time to study our storage modulus, or the elastic behavior, our loss modulus, or the viscous behavior, along with finding the limit of linear viscoelastic region, but we'll see more on that later, or now. In the samples with alkanolamines, we find that we have greater G prime and G double prime, the storage and loss moduli, which is equivalent to a higher stiffness or a lower workability. However, it's not that significant, as significant differences are on orders of magnitude, and these are on the same order of magnitude. We also see a larger linear viscoelastic region in the samples with alkanolamines. So if you look at this flat area on the control sample, it extends to about there, and in the samples with our alkanolamines, they extend to a little bit further down. We also see a curving out behavior in the TEA and DIPA samples. If we look at the very edge of that strain, the high strain area, where the control and TIPA containing samples still go down. The TEA and DIPA samples curve out a little bit. I took the same data and I visualized it a little bit differently. That made more intuitive sense to me. So a stress strain graph, you can see that the increase of linear viscoelastic region equates to a greater yield stress in these samples with the alkanolamines in order of TIPA, DIPA, and TEA. And that curving out behavior that we saw in that other graph looks something like strain hardening in the TEA and DIPA containing samples, which were the ones that behaved similarly in the calorimetry. So these properties might be beneficial in 3D printing applications when we want the layers to hold their own weight and, of course, the layers above. And then finally, we're wondering, why do we see these changes? So we decided to look at SEM, and this is current work right now. We know in Portland cement, the addition of alkanolamines affect the CSH and calcium hydroxide morphology. However, there's been a lack of agreement about whether or not there are changes in the ettringite morphology. And we saw in the XRD and TGA data again that there may be some poorly crystalline ettringite. So the changes that we see physically may be a result of our differences in morphology. And this is just an example SEM picture that I took of our paste at 2 hours of hydration, where you can see the ettringite. So to sum all of that up, we see that the alkanolamines do affect the hydration of CSAB differently than Portland cement, which is interesting. We saw in the calorimetry that our TEA and DIPA containing samples, they behave similarly, while the DIPA sample behaved more like the control sample. They all, or the TEA and DIPA samples did delay the hydration peak, and they all decreased the total your cumulative heat at the end. We saw in the XRD and TGA that there are changes in your hydration product amount, but these were a little bit different we saw in the XRD than we saw in the TGA, which might allude to some, again, poorly crystalline ettringite. In the rheology, we saw that there was a slight increase in stiffness and a decrease of workability. And there's ongoing work to just link all of these changes to morphology. So through all of that, we saw that there is that possibility to use alkanolamines to tailor our desired properties, so that rheology, the set time, your dimensional stability, and strength. And because, or if these changes are because of ettringite morphology differences, this can extend to other systems that form ettringite too. That's it. I just wanted to acknowledge Dow for their funding, Tom and Jolie for their continued interest and insight, Dr. Curtis and Dr. Wilkinson for their advising, Elsa for her mentorship, and then the Curtis group, and pointing out Barak specifically because he helped me a lot with the rheology. Thank you.